All right, everyone. Hi again for a continuation of the exciting lectures on regression. We are almost done with regression, and I hope that today we'll be done with all of it. And I wanted to just remind you what we did last time, always kind of without even referring to equations, just thinking about things. So the standard methodology of deriving least squares regression was to just go in by hand and define your model that you want to fit the data onto. It has a bunch of coefficients. The coefficients have to show up linearly. So, ax squared plus b cosine x, for example. As long as the coefficients are linear, show up linearly themselves, then you are doing linear regression. You define the error norm, which is the difference between your model applied to the input independent variables. And when you apply that, you get y values, and when you take the difference between the model y values and the observed y values, then you get an error. You take the sum of all of those errors, the square of the sum of the squares, and then you minimize that summation. Okay, so and then to minimize it, because you're fitting the coefficients, you differentiate that sum with respect to the coefficients, and you get your system of equations that governs what the coefficients need to be. And once you solve that, that will minimize the summation, that error summation. And then last time we said, okay, this can get really complicated. This coefficient matrix that you need to solve is really annoying to derive by hand, especially if your model doesn't fit a standard polynomial model that Python could do, for example, or some of the few models that Excel provides you with, like a logarithmic or an exponential model, okay? What if you wanted to combine sines and exponentials and logarithms, for example? You would need to do this by hand. And so that makes the derivation very cumbersome. So we talked about another way of deriving the normal equations. Those are the equations that govern regression. We call them the normal equations. And that methodology focuses essentially on showing that all you need to do is define this matrix that has all the basis functions of your model. So one other thing we defined last time was every model, you write it as a coefficient times a basis function. So this could be x, this phi one could be x, this could be x cubed or cosine x, etc. It turns out if you can just define this matrix A, where the columns correspond to which basis function you're at. So first column, first basis function, second column is second basis function, and so on. And the rows correspond to the observations at which those basis functions are evaluated. So first observation, the number of observations depends on how much data you have. Okay, so you're given xi, yi values, right? So you just simply apply your basis functions on those xi values. And I claim that once you know A, then that's it. You have a governing system of equations, which is a linear system of equations in this case, for linear regression. And that system looks like A transpose A unknowns, we call that alpha, contains the coefficients, equal A transpose times yi, the yi vector, the right-hand side values. I'm going to show you a really cool way of doing this complex matrix. So this matrix is still complex. It's easier conceptually to write it down and put it together, right? But programming it is still a little bit might be cumbersome. But there's a really neat way of doing this in Python using NumPy. You can do it with other libraries, but I'm going to show you just the NumPy way, and you can just take that and fly with it as you move on in your career. If you learn another way, go ahead and do that. And that methodology and that approach is called NumPy is called column stack. And what it does, it creates columns, okay, based on just one-dimensional array. So if you think of this first column, it's the first basis functions evaluated at x1, x2, x3, and so on to the nth observation. So that array, you want to be able to put that array in the first column. You want to be able to put the second array in the second column, and that corresponds to the second basis function, right? And if you evaluate the second basis function on x1, x2, and so on, that gives you an array, and you put that over here. So you do this with column stack. All you have to do is if you have your function, basis function could be sine, cosine, logarithm, exponential, x, right? Just apply it at the all the observations. So phi1 of xi gives you an array, a one-dimensional array of phi1 evaluated at x1 and evaluated at x2 and x3 and so on. So it gives you this first column. Okay, same thing for phi2 and so on. Now to stack them like this, you use a numpy.column stack, and that's it. So all you need to know are the basis functions, really. And in Python, so to extend this further, you define A as numpy.column stack all your basis functions. Sorry, you cannot see my hand. And then you define the coefficient matrix of regression. I call that ATA. That's A transpose A. If you look at this line, it's A dot T that gives you the transpose of A. At A, that's the matrix multiplication. Remember, we had looked at this at symbol, which is matrix multiplication. So A dot TA, that gives you ATA. That's the left-hand side of the system of equations. And then the right-hand side is simply the transpose of A multiplied by the yi values. So that's A dot T at yi values. And then you solve the system just simply using Lin algebra.solve. We're not going to use any of the fancy iterative solvers we use because these are generally systems that are very dense. So, and I'd rather use just the built-in matrix given built-in solver in Python. Okay, a couple of examples here, and we'll do this in Python together. So for example, if your model equation was a straight line, so A plus BX, then your A matrix looks like 1x1, 1x2, and so on. So in the first column, we want to stack a bunch of ones, and in the second column, we want to stack a bunch of the array of x1, x2, and so on. So what I do here is A is numpy.column stack, and the first column, I want an array of ones, and that's just simply numpy.ones of size n. And in the second one, I just want the array of xi, and that's given to me. So I just put in xi, as you can see in the code, and then the rest is similar. Now, if you were to do a quadratic, for example, you get 1x1 and 1x and x squared. So in your column stack, you want to have ones in the first column, you want to have xi's in the second column, and xi squared in the third column. Okay. Now, this is really cool because once you know A, the rest is just standard. You don't have to even change your code because ATA and ATYI, all you have to do is change your XI and your A, and then the fitting via regression is the same, okay? So I want you to go ahead now and download from the Canvas modules or under files, there's Jupyter Notebooks regression. I want you to download the regression activity 2, the normal equations university GPA example with gaps. And don't forget to tag along another data file called gpa-data.txt. We're gonna pull up these GPA data from students, and we're gonna try to regress them. We're gonna look at trying to predict and correlate university GPA with high school GPA. All right. I will see you on the other side. All right, I am back over here, and I am going to share the screen with you now in Zoom. Okay. So this is all being recorded on YouTube, but now I want you to just follow with me on Zoom. But when you review, all of the activity will be recorded on the stream, okay? And I'm gonna share my screen, desktop 3. Okay, can you see my screen? I shared my screen, can you see it?
Yeah.
Thank you, okay, great. And is this Zoom level acceptable? Yeah? Excellent. All right, so go ahead and download this file, and along with it, download the gpa-data.txt, okay, and put them in the same directory next to each other, okay? I'll give you another second. Anyone still working on this? So now we're going to do regression on these data using this new approach of deriving the normal equations. Let's call it just the regression matrix, or the new way of deriving the normal equations without using the least squares. So in a question, in a homework problem or exam, I will be specific. I'll tell you, do not minimize the sum of the squares. Okay, so when I say that, I mean use the matrix, how we built it from the basis functions. But I might ask you to use specifically the least squares, minimizing the summation of the error. Okay, so I'm assuming you all got this notebook. All right, so go ahead and execute the boilerplate. In this first cell, I got import numpy and the magic matplotlib. Let me make sure this is the one, okay. And in the second cell, I have this function called r squared. Feel free to use this function as we move along in your homework. What this function does is that it computes the r squared value for the regression. And to compute the r squared value, remember we needed the mean and a bunch of other things. So I boiled it down to a very simple function call. And that function simply takes in the xi and yi values. Those are your input independent and input dependent variables, and also takes the y model. I will discuss this in a second. So that y model is going to be a function call for your regression model. It's really cool, so that we can calculate the r squared independently of being specific to a particular regression model. Okay, I'll discuss this once we get there. All right, so first I want to import the data. Don't worry about what I'm doing here with the data. I had to import it and take the transpose and a bunch of other things. Just execute those cells. What this first one does is that it loads the GPA data.txt and puts it in a very big data structure called data. Okay, and I know, because I got those data from the internet, I know how those data look like. And I know that the high school GPA is contained in data 0 in the first column of data, and university GPA is contained in the fifth column of data. Okay, and so now you can simply, if you type high school GPA, just get a bunch of numbers, and if you print out the university GPA, you get another bunch of numbers. Okay, so we're gonna try to see if we can do a prediction of your university GPA based on your high school GPA. All right. Now the next step, I always do this so that I don't have to change my variable names. Once I bring the data, give it names, etc., I almost always identify which are the x values and which are the y values. Okay, in this case, my x values, I'm gonna call them xi. Those are the high school GPA data, and my yi values are the university GPA. All on board? Okay, anyone disagrees? Excellent. All right, what do we do when we have data? I want you all to scream. We plot it. All right, we flirt with it, we plot it. All right, and let's plot it. This is what we've got. So what I have here is, on the y-axis, we have the university GPA. On the x-axis is the high school GPA, and I plot a scatter, right? So imagine you had done straight lines over here, you know, without the scatter. Look at how it's gonna look like. It doesn't make sense at all. That's why you need to put, always when you have discrete data, always start with a symbol. Now this makes sense, right? X values, Y values. You might have multiple Y values for the same X value, right? Because two students might have the same high school GPA, but they might have a different university GPA. Okay, we're gonna see if we can make a prediction on your university GPA now. Now you see the data has a trend. It looks like a funnel, right? Like a funnel, but as your high school GPA increases, there's a clear trend that your university GPA increases. Okay, so that's a fact. So if you're really good at school, you're most likely to be really good at university. Okay, now for the lower GPAs, that's where things become interesting. Where, you know, if you have a lower GPA, that might not necessarily indicate your high school GPA, because many of us you know, I myself included, I used to be horrible with math because it didn't click with me, because it was always thrown at me without a decent and deep explanation. It was like, just memorize this, and I never did well. Once I went to university, you know, I started understanding things better, and I became way better at math. And so this is an example of this, where, you know, your high school performance in math, for example, or physics might not have been really good, but once you come to university, things start clicking, or you meet a better teacher, for example. Okay. All right, so now we want to try to do a straight line regression. I mean, really, the best thing you could do here is probably just a straight line regression, because the data also, although it's a funnel, it's kind of pointing in one direction. It looks like the tip of an arrow, really. All right, so we're going to start by doing a straight line regression, and for the straight line model, this is what we've got. This is the A matrix. 1x1, 1x2. It's written incorrectly here. Honestly, this shouldn't be written this way. It should not be written this way. Let me correct this. The A matrix should just be the A matrix. Okay. So this is your A matrix, ones and x1, x2, etc. And now what I need to do is, based on the column stack methodology, is just simply define the first column and the second column. The first column is a bunch of ones, and there's n of those, correct? And that's why I defined n as the length of the number of observations I have. And then simply in the first column, I created a one-dimensional array of ones. Remember, np.ones gives you ones of size, whatever you give it. Here I'm giving it n. xi itself is an array containing x1, x2, x3. So when I do this, I claim that I get this array. Okay, let me print it out. It might not print nicely, but if you look at this, right? This is what we have. Don't you agree that this is my A matrix? It's got ones in the first column and x1, x2, and so on in the second column. So that's good. Let's delete this. Now simply, I define my system is A transpose A for the left-hand side and A transpose B for the right-hand side. So I define ATA as the coefficient matrix. It's A transpose at A, and the right-hand side is A transpose at YI. I enter this, and now I solve the system of equations. Okay. Now, okay, let me ask you this. What is the size of ATA? Is it a 100 by 100? Think about this. Sammy.
It would be 2 by n, right?
2 by
N.
Why?
Because it's just the original one flipped sideways.
But multiplied by the original one. So ATA is the product of the transpose of A by A. So think about this. This is a system. Let's think intuitively. We're doing a straight line fit. How many unknowns do we have for this straight line fit? Abby?
2 by 2,
Yeah.
because you have 2 unknowns.
Yeah, we should expect a 2 by 2 system of equations, because we are solving for two unknowns. Those are the coefficients A0 and A1, correct? So we should expect two equations by two unknowns. And then your system of equations is simply 2 by 2. So let me print ATA. Look at that. It's an array of 2 by 2. Remember when we did the straight line regression in the beginning, what we ended up having a system of 2 by 2. It had like n and summation of xi, whatever summation of xi and summation of xi squared, right? This is it. Okay. Now, when you solve this, you get the coefficients A0 and A1. Now, the standard way I've been doing this is to simply grab the coefficients from your solution, where I put the linear algebra solve. I solve coefficient, matrix, right-hand side, I got the solution. The solution contains A0 and A1 in that order. And then I pull those from solution. So solution is a array, two values, A0 and A1. The first entry in solution is A0. The second entry is A1. And then I define my model as a linear fit. I call it linear fit, A0 plus A1x, so that I'm able to make a prediction, okay? And then we plot the original data and plot the linear fit as well, and this is what we get. All right, so now give me your high school GPA, or punch in your high school GPA and see if your current university GPA is consistent with this prediction. If anyone wants to share, go ahead and share.
Mine isn't very consistent.
Okay.
I had a 3.2 in high school, and now I have a 3.6.
Okay.
And it says I should have a 3.25.
Yeah. Okay. But remember, Jeremy, that you're not done with university. So, right? So these data are based on when you're done. Now, I think your GPA is going to continue increasing. So, so it might not be a very good prediction. I agree, but let's see some other numbers. Who's got a consistent or inconsistent?
That's fairly close. I had a 3.98 in high school, and I have a 4 right now, so I'm getting a 3.996.
Okay, yeah, and we kind of knew that, right? Because on the upper right, all the data clusters together, but it's the intermediate or the lower left that you're going to see a lot of variation in it, right? So Jeremy was at 3.2. That's just somewhere over here. You have a lot of variance over there, okay? You have a lot of spread of the data around that straight line, especially for the GPAs between 2 and 3. There's a lot of spread. Okay, so how do we evaluate our prediction? We calculate the R2 value. So I don't have a high school GPA because where I grew up, we didn't have the concept of GPA. You know, we don't simplify people to a simple number, but anyway, the R squared value, it gives us an idea of how good our fit is. Now, remember, I told you this function signature takes in xi and yi values, and then it takes your model. And that model is simply your function that you just defined over here. Okay, see, I call it linear fit. And when I print this, oops, R squared is not executed. Hold on. Okay, let me execute R squared. It gives me a 60% R squared value. It's not a good fit. But I do tell you, if you had chopped the data from 3.25 to 4 high school GPA, it will be a good fit. Okay, it's just early on, there's significant spread in the data. It can really, there's nothing we can do over there. All right, so now I want you to try to do a quadratic fit. Okay, go ahead and fill in the blanks. This is the regression matrix, or the new way of doing the normal equations. Okay, go ahead and fill in the blanks. right, anyone done with the first?
Yeah, so the first one is gonna be NP once N, comma XI, comma XI squared.
Okay, excellent, Sovit. Thank you so much. That's great. Everyone
Thank
got
you.
that? All right, now who wants to give me the second one? Sovit, do you want to continue?
Yeah, so it's going to be the same thing like it's going to be A transpose at A, that is a multiplied by A, and the second one is A transpose multiplied by YI.
Correct. Excellent. And this is what you got. So those are the coefficients of the polynomial. Okay. Now, what is the size of ATA? Abby, I see you moving your fingers, but I can't hear you.
Oh, it's 3 by 3.
Okay.
This time.
Right? Okay. It is 3 by 3. Indeed. So that's a good check, right? This is another example of critical thinking. Like, make a prediction in your mind. What do I expect this to be? Let me look at it, make sure everything is okay. At least the logic of it is consistent, okay? All right, now we pull out our coefficients from the solution, and then we define a quad fit, which is a0 plus a1x plus a2x squared. And then we go ahead and plot the data. Oh, we've got the wrong thing over here. I'm going to plot xi and then quad fit applied on xi. Do you expect this to do any better? No, I don't expect this to do any better because the data is really not. It's. I don't know what the data. It's weird. It doesn't have. Best thing would be linear. I cannot think of any other function that would do better than a straight line. And indeed, we get a 60%, almost the same as the straight line fit for the R-squared value. Okay. All right. Let's go ahead and switch back to continue the lecture and see what's next for us. All right. I'm gonna stop the share, and I'm gonna. All right, as we just saw, it's really straightforward. Once you know, it's really straightforward to do regression once you know how to build this A matrix, this regression matrix. All you need are your basis functions, and then the rest is history. You can use what we did in class, you can build on it, improve it, compare it with NumPy regression, but to build non-standard polynomial models, you gotta do this by hand every time. All right, now the next step is looking at nonlinear regression. And we're not going to be able to solve nonlinear regression models yet, but I want to show you that we can do them because the idea of minimizing the error is the same, whatever model you use. All right. So first, let's ask a question: what makes a regression model linear, and what makes it nonlinear? We kind of have a hint about that. And eventually you develop a feel that the coefficients show up linearly, but I'm going to give you a couple of tricks to think about how you can identify whether a model is linear or not. By definition, the regression model is linear if the resulting equations governing the unknown coefficients is a system of linear equations. It will always be a system of equations, okay, whether linear or not, it will always be a system of equations. But if it's a linear system of equations, in other words, the unknowns show up in a linear fashion, or you can write it as a matrix vector multiplication, then that is linear regression. So you can do this by hand. You can do this in two ways. Either write the least squares equations, which entails a lot of algebra, and then show that you get a system of equations, or look at the recent methodology that we developed, see if you can stack the basis functions, separate those from the coefficients. That gives you a very quick way of figuring out whether your model is regression or is linear or not. All right. So I'll give you an example. For example, this model is the standard model ax plus b. The least squares equation gives us this. This is method 1 of figuring out whether you get linear regression or not. And the normal equations, you just simply write out the basis functions, separate those from a and b, and this is what you get. Okay. Now I have an activity for you. I have a bunch of models over here, and I want you to spend some time. Clearly, you're not going to do the least squares derivation. I think it's easier to just see if you can if you can pull out this A matrix out of all of these models. So go ahead and spend a couple of minutes, and I will see you on Zoom. We can discuss if these models are linear or not. All right, I am back on Zoom. You can still see the slide on the YouTube stream. But please listen to me through Zoom, not YouTube. Can you see it okay on YouTube, or do you want it a little bit more maximum, a little bit bigger?
Bigger would be nice, if possible.
Okay, let me try this. You can try to maximize your window. Is this okay, Sammy? Should take a second to show up on YouTube.
Yeah, that's good, thanks.
Okay. In the intuitive way for me, when I look at these models, I just see if the coefficient is inside a nonlinear function and it cannot be separated from it. But there's a trick sometimes. If, like, let's say you have a constant inside a log, so you have log ax, okay, then you can separate that log a, right, plus log x, and then log a becomes a constant. But if I had log a plus x, for example, then that is clearly nonlinear. So even if you're writing the normal equations and the basis functions, you're going to have to separate, okay? Simplify the functions that you can. In the meantime, I'm going to pull up the wheel of misfortune. All right. I think some of you already have some answers. Let's start spinning the wheel. All right, Hayden, are you with us today? Not with us. Okay, Megan. All right, I'll do one more and then I'll just start picking from the screen randomly. Anna, are you with us? All right, so I'm just gonna pick randomly from the screen. All right, let me see. Carson, do you want to try this? Try the first two. The first one, we know it's linear. The second one.
Yeah, sure. I'm guessing that the I'm not great at this right now. I'm still trying to kind of figure it out. I think the second one is nonlinear because the wait, but you could pull the B out. I think the second one's linear.
Correct. Yeah.
And the
Yep.
the third one.
Hold on. Let me ask someone else. Jessica.
Okay, sorry. Never mind.
Thanks, Carson. Jessica, do you want to take the third one? Okay. Natalie, do you want to take the third one?
Linear.
Okay, yeah, because sine A is just a constant, right? Although we wrote it as sine of A, that whole thing is just a value once we solve for it, right? Now, what about the one below it, sine of AX plus B? Let's see, Max.
Yeah, it's nonlinear.
Yeah, do you want to elaborate a little bit?
The coefficient is inside the parenthesis with the sign, so it would be, yeah.
Yeah, and because of the way the sign is built, the sign nature of the sign function, you cannot separate that into sine A and sine X, right? It's really complicated. It's not like the log AX, okay? All right, let's see the one below it, AX all squared plus B, Corwin? And if you had selected not to be picked on, I'm sorry, just let me know. I don't
No. I just didn't have like which ones I wrote down. Like I wrote them down, just not and indicate which one was which. So I had that one as linear, I think.
Yeah. Why?
Because the A value is squared, so that's just a constant
Agreed.
on its own.
Yes, yeah. So you just get something of the form constant x squared plus b. All right, let's do the one below it, x to the a plus b. Dylan, are you with us?
Yes, yeah.
Yeah.
I think that one's going to be nonlinear.
Agreed. Yeah, there's no way to just pull out that a and make it multiply the basis function, okay? There's no way to do that. Now the one below it, a to the power x plus b. Let's see. All right, Abby.
Yeah, so the one where it's
a to the x plus b.
A to the x plus b. I said nonlinear because you can't separate the x and the a.
Yeah, you cannot separate the basis function from the coefficient, right? Okay, the one below it, let's see. I'm getting to my, hey, Weston, do you want to take the e to the alpha times x plus beta x squared?
Yeah, of course. I put it as linear because you can separate the base function and the coefficients.
Absolutely correct. Beautiful. All right, one last one. Sean, beta e to the alpha x.
I would say that's nonlinear.
Correct. Yeah, because e to the alpha, even if you call e to the alpha, make it a constant, it's still going to be to the power x, which is nonlinear. All right, so I'll see you the other side and I'll explain this a little bit more, okay? All right, so you all nailed it. We nailed it together. So indeed, the first one, second one, third one, they're linear because you can separate the coefficient and the basis function. This sine ax plus b is nonlinear because you cannot separate a or sine a and multiply it by another. The basis function contains this coefficient. All right. This particular function is helpful because sometimes you also need to fit the frequency of a certain data set, not just the amplitude, right? If you had a coefficient outside the sine and cosine. Ax all squared plus b, it's linear because you can separate a squared out of the basis function x squared, And x to the b, x to the a plus b is nonlinear because you can't separate the constant. Same thing with a to the power x. This one is linear. E to the alpha is just a constant, okay? It's just going to be a constant. It multiplies the basis function. So our basis functions in this model are x and x squared. Last one is nonlinear. You cannot separate the basis functions from the coefficient. And I have a detailed explanation here showing you how I would write this into the recent methodology that we developed for the normal equations. So clearly you can see how we can separate the basis functions and the coefficients. Same thing for this one, ax plus b1 over x. So 1 over x and x, they're the basis functions. Over here, the basis functions are 1 and x. This one is nonlinear. We cannot separate the basis function from the coefficient. And all of these are also, well, this one is linear because ax squared is a squared x squared, and that's ax squared plus b. Basis functions are x squared and 1. And same thing here, basis functions are x and x squared, and we can separate the coefficients. And finally, all of these guys over here are nonlinear, okay? Now, in many cases, before we get to the final piece of information in this chapter, in many cases, we can turn certain nonlinear models, okay, into linear models, okay? But you have to do a transformation. You have to do an operation on the model itself, okay? You got to apply something to transform it into something linear. This is more of an art in general than it is an art that is based on your experience with models. So we cannot give you just one single formula for all of the models out there. But as you see more models, you can start you can start learning how to do algebraic manipulation to turn some nonlinear models into linear ones. The classic the classic transformation of a nonlinear model is this one, is of the form alpha e to the beta something f of x. So a classic example of this is the reaction rate constant in kinetics, and that's k of t, that's a function of the temperature, is equal to a coefficient a called the pre-exponential factor e to the minus some activation energy times 1 over RT, that's gas constant and temperature. Okay, so this whole thing, 1 over RT, that's your function of temperature. Okay, that's the equivalent of f of x over here. And your unknowns are A and E. Okay, now in this particular case, we can do a transformation and make this linear. Okay, by using a very nice property of the logarithm. If you take the logarithm of your model on the left-hand side and apply it on the right-hand side as well, you can separate alpha and e to the beta f of x, and what you get log alpha plus beta f of x. Now you've transformed your original model into a new model that is what? Linear. So now your new model, you can just call it capital Y model, is equal to a constant plus another constant times this entire basis function over here, f of x, okay? The point is that you could separate the basis function from the coefficients by taking the logarithm. And then your new model is simply a straight line, okay? Now, to go back to the original model, you got to be able to translate, because the original model we were looking for, in this case, we were looking for A and E, right? But we transformed everything into A naught plus A1 x, then you can simply translate back and forth between the two models, okay? Based on what you've done. So in the general case, A naught was log alpha. So if you want alpha, you got to take the exponential of A naught, and your beta was simply A1, and your capital X is your whatever function you have over here, okay? Here's a classic example that I just gave actually. It's the reaction rate constant, and it looks like this. We're going to do this example in Python together. So you are given data in this case, if it wasn't clear to you, are given data K versus temperature. So at different, you got some reaction going on. Okay, I think there's a benzene example over here, but you're given data and the reaction rate, you're given data of some reaction going on. And how fast that reaction is progressing is dependent on the temperature, and that's the formula for that. But the point is you're given data of the reaction constant and the temperature. Okay, so you have those data. So your xi's would be the temperature, and your yi's would be the K. And your goal is to find A and E. okay, the activation function. Then we take the logarithm, like I said, so you get log k. So you have to transform your input data, okay, and we'll see that in a second in Python. And then you turn that into a regression. So let's go ahead and do this together in class, okay? Regression activity 3, go ahead and download the regression activity 3 nonlinear model rate constant with gaps. Okay, there's no data to import here. It's all inside the notebook. We'll go ahead and do this together. You might have to refer to the slides to wrap your head around what's going on, because we're going to go back and forth between the original model and the new model, the logarithm. All right? All right, I am back on Zoom, and go ahead and download the notebook. Okay, give you a second. You can find it either on files in Canvas or on the in the modules. Okay. So now we are in Zoom. I'm still streaming on YouTube for you to read through that later. Okay. And listen to that later. All right. Anyone still loading up that notebook? All right, let's go ahead and get started. Again, I got some boilerplate stuff, NumPy, Matplotlib, etc. And I also wanted to define the R squared, okay? The R squared function to be able to calculate the R squared. Now, the data is given to us as temperature, a bunch of temperatures. We got 1, 2, 3, 4, 5 data points, and a bunch of reaction rates, and in a universal gas constant, okay? Or we are gonna need this. Now, first thing to do is plot the data. So what do we wanna plot? We wanna plot K versus T. So on the x-axis, we have T, and the y-axis, we have K. So if I plot this, you get this nice exponential trend, okay? And that's why the model for these data is an exponential model, but it's of the form alpha e to the beta some function, okay? Now, this is our model. Like I said, K is A e to the minus some number EA over RT. We don't know what A and E are, and we want to fit those to be able to make predictions for, other temperatures. So in this case, what are our XI values? Like I said in the previous notebook, first thing I do is always put everything in a standard form of xi, yi. So I'm always thinking in terms of independent xi and dependent yi, okay? So what are our xi values in this case? Let's see, James.
Is it the temperatures?
Yep, it's the T. And what about the yi?
K.
Okay, correct. So those are, we just plotted those really. So those are our independent variable and dependent variable. And to just make sure that we got this right, this is exactly what we have. All right, so we're gonna do now a straight line fit with the normal equations, okay? But the problem here is that, okay, so hold on a second. We need to first convert the data, and I did not have this discussion over here. Okay, I did not have this discussion over here. So let me bring in my slides over here to show you the math of what we need to do. Okay, so look at this. You're still looking at the shared screen in Zoom, right? So remember, our original model was K A e to the minus EA over RT. We can't fit that with linear regression. We can do it with nonlinear regression. We'll learn that later. But with linear regression, we cannot do this. We have to first transform it. So we need to take the logarithm of both sides so that this is the new equation that we are solving. Okay, so if you take the logarithm, the new y values are, the original y values were K, okay? but the new y values are log k. The original x values were just the temperature. But what are the new x values? They are -1 over RT. Do you agree? Okay. So what I'm going to do actually, I'm going to write this. I'm going to put this over here. So xi is going to be the -1 over RT. Okay. And yi's, the new yi's are going to be mp.log k. Now, when I plot those, look what happens. It is a straight line. Okay? It is a straight line. And that's expected because the data was exponential. You take the logarithm, it's just going to become a straight line. Okay, it's like doing it on a log-log plot. Now we're going to fit the normal equations. Now we're going to do the normal equations. And for the normal equations, all you need is to do a column stack. For a straight line, you need 1's and xi's, right? So anyone would like to help me here? Once you converted your model, we took the logarithm, forget about it. Just deal with the new xi and the new yi. Okay, forget about the original data. Okay, we're just working as if we have this new data, a straight line. All right. Sammy, do you want to help me with this?
Sure. So for the first spot, I did np.ones with an n, length of n. And then the second one is just xi.
Okay. And if you print A, this is what you get. Now notice this xi is not the original independent variables, right, which were the temperatures. These are the transformed ones. And based on the math, those are -1 over RT. See this new x over here? Now we do ATA. So I'm just going to go ahead and do it. A transpose A. And then the right-hand side, call it right-hand side. I call it B, call it right-hand side, is A transpose times the new, the yi values. Okay? Solve the system of equations. We're going to solve ATA and right-hand side. And this is our solution. These are the coefficients, A0 and A1. Then we do the same thing we did in the previous notebook. I don't know why my labels are messed up over here. Now look at that fit. It fits the transformed data directly because the transformed data was linear as expected, and a straight line fit is going to fit that directly. It's not going to go through each and every point because that's not interpolation. This is regression. So it kind of sits in between. There's some variation between the points. And we can calculate the R squared value. It's 99.9%. It's like almost doctored. Any R squared value that looks like that, you have to be a little bit suspicious of it. Okay. All right. So now I want to take, now we found our C0 and C1 in this equation, in the transformed equation. I want to take those and convert back to the original model to find A and EA. And simply the relation C0 is simply log of A. So therefore A is exponential of C0 if I want to go back to the original model. And EA is simply C1. And that's what I want to do here. The original, let me call it A, the pre-exponential factor, is the exponential of C0, that coefficient that we calculated here. And EA is simply C1. And this is our new logarithmic function that was taken after we did the transformation. We did regression on the transformation, and then we put this back into the original form. And then we're going to plot it. And this is what you get. So this is an example of doing a nonlinear model, transforming it into a linear model, regressing the transformed model, and then going back. Okay? And then going back. Any issues? Any concerns?
I just had a quick question, if you don't mind, Professor.
Yeah, of course, of course.
So in the last activity, you said that a 60% fit line was bad, but a 99% line is too good. So what would be the just right in that case?
I don't know. I mean, I am skeptical. Anything is just too good to be true, right? 99.99 is just too good to be true. Okay, it's rare in life to see such nice trends. Now, in the hard sciences, like in physics and engineering, there are systems that behave this way, or specifically for this model, it might be the case that, yeah, this is true, but I would be suspicious. Okay, there's no guideline. Like, what I would be comfortable with a 98% fit, 96% fit. You know, there's an error in there. You got to see some error, some variation. Right. So when I'm reviewing a paper with data, for example, that is this good, too good to be true, I'm like, yeah, you know, did you guys repeat your experiments, measure under different conditions, you know, account for user error and so on, or did you doctor the data? So it's not an accusation, but it's just healthy skepticism. Okay. So that's the message here. Be skeptical, even if you got the 60%. So let's say you get 60% with data that is like a straight line. Then something is wrong. Then your fit is wrong, right? So be skeptical of everything. You know, a healthy skepticism is good. Okay. All right. Okay, let's switch back to finish off this lecture series. And then I think Mitchell had a life hack for us for today. All right, we'll see you on the other side. All right, now that you've seen how we can convert one example of a nonlinear model into a linear model and then regress the linear model and then go back to the original fit, in your homework, you'll be doing a couple of other examples like this. It's just a matter of looking at the algebra a little bit differently, okay? And feel free to manipulate your model. You know, like if you had k equals something over something, feel free to do 1 over k, or take a logarithm, or take some function, some transformation that will render your model linear. Last thing I want to talk about is nonlinear least squares regression, to show you that you are able to derive the equations for nonlinear regression. You don't know how to solve them yet, but you know how to derive them, and I expect you to know how to derive them. Okay. So now assume that you have a nonlinear model, such as the ones we described in the table, or this is an example of one. Cosine a naught x plus e to the minus a1 x squared plus sine a2 x squared. Okay, this is a healthy nonlinear model. There's no transformation that will make this linear. You gotta be able, and you wanna regress this. So in other words, when we say regress this, you want to find a naught, a1, and a2 that best fit the data by minimizing the error. In general, the way we describe this, assume that your model F has n parameters, a sub k, so a naught, a1, a2, you know, or a1, a2, all the way to an, okay? Now, the idea of regression is the same. You still want to minimize this sum, which is the difference between the observed y values and the y values of your model applied at the measured x values, right? You still need to minimize this summation, and the way to minimize it is simply by taking ds by dA, or differentiating the sum with respect to each one of the unknown coefficients and setting that equal to 0. So in this case, you would have 3 of those equations, ds by dA naught and ds by dA1, ds by dA2, okay? But you gotta form the summation, and then it's just a matter of taking derivatives, okay? But now what you're gonna end up with is a system of nonlinear equations. And I'll give you an example. So take this example that we just linearized, okay? it's easier to do the linearization because you can do it back of the envelope in an airplane, okay, or when you are on, on a boat and you're stuck on a boat and you don't have a Python. All right, but a nonlinear, if you want to regress the nonlinear model itself, you can do that as well. It's going to be a little bit more expensive when we learn about nonlinear solvers, but you can do it. And you are going to be responsible to deriving the regression equations for a nonlinear model, just the equations. So you define your summation, which is sum of the observed y values minus the model applied at the xi. And there's a typo here. This should be alpha e to the beta xi. Okay, I will correct that before updating the slides, right? But because this is a summation of over all the values, right? And the square of this. Now, you want to minimize this error. You want to find alpha at beta such that this error is minimum. You got to take these two derivatives, okay? And that's it. That's all you have to do to derive the equations. The derivatives are going to be nasty now because the coefficients are inside the nonlinear functions, right? So when you differentiate with respect to beta, you got to take beta e to the beta x, and so you have alpha beta, and it gets a little bit more complicated, okay? And so this is with respect to alpha, the derivative with respect to alpha, derivative with respect to beta. You set those equal to 0, and you get your system of nonlinear equations. Why is this nonlinear? There's no way you can write it. You can write this as coefficients and basis functions. Okay, think of the our basis functions and coefficients separately. And this is a nonlinear system of equations. You cannot separate the unknowns from what is known. Okay. So that's one example. I have another example for you to do at home, just to kind of exercise your derivatives, just simply a matter of taking derivatives. The procedure is the same as before. All you have to do is take those derivatives and build your system of equations. I will ask you in your homework, in your exam, I'll give you a nonlinear model, and I tell you, derive the governing equations of nonlinear regression. In a couple of chapters, we will learn how we do how we solve these nonlinear systems of equations. And with this, we complete our discussion on regression. I had one more example on COVID-19 because of the current situation of what's going on. So go ahead and download this notebook, COVID-19 death in the USA. We're gonna look at the trends of the total number of new deaths, okay, versus the number of days since we started recording those data. So go ahead, download this notebook, and along with it, get the COVID-19 USA data, new death. I picked up this data file about a week ago, okay, so it's very recent. And we'll try to do a regression on it, and then we will do our tips. So it shouldn't take us more than 10 minutes to go through the example. All right, I'll see you on the other side. All right, I am here, my pupils. Okay, I am gonna share my screen with you, and while you go ahead and download the notebook on COVID-19, okay? Hope you can see my screen. I'm gonna zoom in so that Sammy is not upset with me. And download that data file, COVID-19 USA new death.txt, and put it right next to your notebook. I'm gonna pull the data from that, okay? Now, this is a very simplified way of thinking about regression for COVID. That's not how it's supposed to be done, but if you're curious, you can just apply the methods that we learned and see if you can make a prediction. Clearly, a problem like this with COVID-19, there are so many variables going on. So what you would need is multivariate regression, which is a simple extension of what we've done here, except you just have two independent variables to look at, okay? Once we get to ODEs, I'll show you, we will develop together a prediction, a COVID-19 prediction, and look at the effect of of shutdowns. It's really cool, and we will show that complete shutdowns are not better than kind of intermittent shutdowns, like shut down a little bit and then you open up and then shut down and then you open up. So it's really cool once we get to ODs. All right, so let's go ahead and do this least squares with COVID-19 deaths. So go ahead, get the boilerplate out of the way and define the R-squared value. Now simply load up the data from this text file. Just execute these two cells. Excuse me. In xi, I have days, essentially day 0, day 1, day 2, since we started the recording death. And in the yi, I have new recorded death on a certain day, okay? And then when you plot this, this is what you get. So we saw this peak last year, and then then ensuing the shutdown, and then we opened up a little bit again and went up, and then it really got really bad by December, and then now it's really slowing down, thankfully, right? So this is what we've got. It's about 360 days, so that's just about a year from today. Okay, just about a year from today. All right, I want to try to do it. Clearly, a straight line fit is just not going to do anything over here, but we're going to do it. Okay, we're going to try to do it. And I have the system already set up for you here. You solve it, you do all of this, and you do the straight line fit. You get the R-squared value, and it's 30%. It's a terrible, terrible fit, right? Now, I want you to pick any one of the following: quadratic, cubic, fourth order, or come up with your own model, right? So if I were to think of this, there is some sinusoidal behavior, okay? There is some sinusoidal behavior, but the problem is you don't know the frequency. So you might, if you're doing something like a cosine number of days, you got to multiply that number of days by a frequency, but it's not clear what that frequency is, and the amplitude also changes. Initially, you have a high like 3,000 deaths, and then goes down to 1,500, then goes up to 5,000, right? So sine cosine model, be cautious, but pick one of those: quadratic, cubic, fourth order. Think about a property of polynomials. When do polynomials become more oscillatory? At higher order. So we could mimic the oscillatory behavior by using a high order polynomial. Okay, so if I were you, I would just pick one of those and just try to implement the fit. Okay, just copy this line, just copy these two lines. So let's say I am actually gonna try a fifth order fit. Okay, really, I don't have an answer for this. I just got the data and I'm playing with it just like we are doing right now. Okay, so I'm gonna try a non-traditional polynomial. So I'm not gonna have a constant. So I'm gonna try x and x cubed, okay, and x to the fifth, okay, and I'm gonna execute this. Oops, what happened? xi. Do what you will. I'm doing my own thing over here. And then so I'm trying to fit, okay, Professor Saad's fit. Oh, that sounds weird. Professor Saad regression model. Okay, let's try y model is equal to a1x plus a3x cubed plus a5x to the 5. The reason I chose this is to show you that you cannot do this with built-in Python. You have to program this by hand. Okay, so I got my a1 sol 0, a3 is sol 1, and a5 is sol 2. And then I have a1x plus a3 times x cubed plus a5 times x to the 5. Okay, sol 2, and oops. Oh, I didn't solve the system. np.linalgebra.solve. ATA, B. All right. Wow, that was really bad. See the black line? It's really bad. So it's probably because I'm missing a bunch of coefficients over here. So I'm going to add a constant, np.1s of size n, and I'm going to keep the xi. I'm going to do an xi squared, xi cubed, and I'm going to do xi to the fourth. So I'm going to keep all the coefficients, okay? So in other words, I got a naught plus a1x plus a2x squared plus a4 x to the 4, so the full polynomial, okay? You're probably not keeping up with me, and that's okay. Just do your own thing and let me know what you observe. This will become second nature to you the more you do it, okay? The more you do it, the faster you'll be able to accomplish this. Okay, so a1, we have an a0 plus a1x plus a2x squared plus a3x cubed plus a4 x to the 4. Oh, look at that. I'm capturing the trend a little bit better, right? Capturing the trend a little bit better. Or quintic fit, right? It's a quintic fit. All right. Anyone have any comments on this? Did you try one of the models? Were you unsuccessful? Were you successful? Share with me.
I did the cubic model, and when I first tried it, I accidentally did quadratic, and it was really wrong. But then I've added A3 equals Sol 3. And the line fits the data pretty well. Yeah,
it captures the trend. And you see how powerful this stacking is of the normal equation, right? Anyone tried something else? So go home, play with these data. Tell your friends about it, tell your family about it. Like, I'm making a prediction about COVID and we're gonna go down, continue going down, etc., etc. Okay?
Hey, Professor.
Yeah.
Quick question. Just looking at one of the graphs that I did, I ended up doing the fourth order fit. And I see that on my fourth order fit, the point doesn't pass through 0, 0, that best fit line. Is there a way that we can adjust our best fit so that way it would pass through that on day 0 before it happened?
Nope. Okay. You are worrying about minutia that is not significant. Remember, we are doing a trend. We are capturing the trend. We're not trying to find exactly what happened at any day, because this data in and of itself has significant uncertainty. Who knows what these deaths, were they complications from COVID? Were they directly from COVID? Were there comorbidities, etc., etc.? Okay, and so there's anyway uncertainty in those data. So trying to worry about capturing something very specific in the data, and I know you had asked me a question before also with the regression, like how to make it go through like something similar like this. Don't worry about those things, all right? Because again, in the big picture, we are looking at the trend, at capturing the trend. And the trend, we did capture it with this fit, with this fifth order fit. Okay, we did capture it. Forget about the title of the of the plot. It's wrong, but but I wouldn't worry about little things like that, right? What I'm worried about more is trying. The data has significant spread anyway. Whatever line you put through it, it's going to be spread quite widely around that curve, right? What I would worry about is finding a best model rather than making sure it goes through 0, 0. All right. I hope this helps. Okay. All right. Let's see. Are we ready for a life hack from Mitchell? I think it was Mitchell.
Sure. I was thinking about this the other day, going through the things that I picked up over the years, and it occurred to me the day we are finally starting to get some warmer weather, starting to push winter behind us, since we're getting into March. And I thought about my own. The car that I drive has a black interior, so in the summer it gets really, really hot. And so I had come across this tip on Reddit, and what you do is you open one of the doors, and then you go to the door on the other side, and you use it like a pump. You open and close the door rapidly, and it'll push out a good portion of the hot air a lot faster. Because if you're like me and you're kind of an idiot, you forget to roll down your windows a couple inches, and then you go out to your black car and you kind of just hate life as you sit there in the heat waiting for it to cool down. And this is actually something that really works. If you can use your doors like a pump to push out the hot air, and it'll make it a lot easier, a lot quicker. So there's my life hack for you.
That's a really great hack. Hey, I love it. I actually relate to that. So the first car I bought that had an AC in it was when I came to the US in 2005. It was a brand from Ford called Mercury. And I had an AC. I was like, this is amazing. It's got an AC, so I can ramp, and I had remote start, so I can restart it remotely. But, you know, all the cars I owned before did not have air conditioning. And I grew up on the Mediterranean, and it's very humid. It gets really hot and humid in the summer. So I had that same exact problem. I wish I knew that tip when I was growing up there. That's a great tip. I used to spray to get these water bottles and to aerosolize the water in it to absorb all the heat and evaporate. That's one other way of doing it, but this is really cool. You just open the door, pump out the hot air, and you're done.
Yeah, you kind of look like an idiot while you're doing it, just opening and closing your doors, but it really does work and it does help.
That's great, Michelle. All right, who wants to volunteer next Tuesday?
I got one.
All right, Porter, you're up for next Tuesday. Okay.
Sounds good.
All right, everyone. Hey, thank you so much. Have a great weekend. I'll post the homework in a little bit. Okay. Bye-bye.